Let me know when we're up.
Okay, welcome everybody. It looks like we are live for another Baseline show.
Yes, thank you. Thanks for joining our live studio audience or tuning in on YouTube. We have zkPass joining us today. I was lucky enough to meet the team at ETH Denver at a brunch, and we got talking about the world of zk and identity and the work going on there. So of course we had to bring them on to the show and learn what they're up to. So they'll walk us through a presentation and we'll have some time for a Q&A at the end. So feel free to send your messages in chat and we'll make sure to answer them when we get to that section. Over to you, Annie.
Thanks so much, Sona, for the invite to the Baseline show, and so happy to share with you guys what us here at zkPass are doing. And let me just pull up the deck and let me know if it's showing. 1 second. Okay.
Yes, it is. Now it is. Okay,
perfect. So what I'm going to do is I'm going to go through our deck quickly. It takes about 15 minutes, and then we're going to show you an MVP demo, which give you a pretty straightforward idea of what we're trying to build. And then we'll start the Q&A from there, if that's okay. Yep. So us here at zkPass, we are trying to build a composable identity protocol that's based on multi-party computation, as well as zk-proof technology. So essentially what we're trying to do is to leverage zero knowledge attestation from not just Web3 world, but also Web2 world. And what does that mean? If I'm telling you guys, my name is Annie, I'm over 25 years old, I'm of Australian nationality, I graduated from LSE, and I'm a founding member of zkPass. And besides that, I own a Porsche. Would you believe me? Maybe yes, maybe not. If you do, great. But if you don't believe what I said, you probably want to verify whether what I said was true. And how are we doing that in the old Web2 world? So very likely, in order to prove that I'm Australian, I'm over 25 years old, I need to show you my passport bio page. I need to submit a scanned copy of that. And what that means is, you're overly disclosing your private information, because you're essentially telling them not just the fact that you're over 25, but exactly how old you are and your place of birth, your passport expiration date, et cetera, et cetera. That's, you're essentially telling them a lot more than what they needed to know. And not just that, once you click that submit button, your private data is essentially out of your hand. It resides with a centralized platform that needs to verify your information, or it's with some other third-party KYC agent that they engage with to verify your identity. So that's the problem we have with the current Web2 world way of verifying. And what we think, some of the problem that the Web3 world has is that we have only limited data source, despite the fact that we do have a lot of on-chain data. But when it comes to identity, a lot of the data still resides within the Web2 world. So hence, we think that, a lot of the issues with Web3 kind of purely Web3 identity solution is that they have quite limited data source, and they can't really expand into, the Web2 world with a lot more than, just your on-chain data. And on the right-hand side, we have, a lot of the stats of how many data breaches there are each year and how costly they are. And we all know that on social platforms like LinkedIn or, even dating apps, there are over 30%, 40% fake profiles. So we believe that an ideal Web3 verification should have below 4 features. And that's exactly what we're building zkPass on. First, privacy preserving. Your personal data should be controlled by you and yourself only, and should only be selectively disclosed on a need-to-know basis. Second, verifiable. We have a decentralized ZK nodes network to make sure of that. Compatibility. right? This is what we reckon sets us apart from a lot of our competitors. And I'll mention that more in details, but essentially because we redesigned TLS, and that has enabled us to be license free and making us very, very compatible. We can be compatible to over 99% of the Web 2 and Web 3 data source. And essentially everything that's HTTP based, web page based, we can verify. And last but not least, anti-cheating. We have a mechanism to prevent the credential holder from tampering with their data. So for example, if I want to lie about my age, I can probably get away with photoshopping my, passport bio page and still send through, to get verified, and that'll likely work. But in our way of verifying, because we are essentially getting the verification results straight from a trustworthy data source, and through multi-party computation, we make sure that the credential holder or the prover will not be able to tamper with that data. So just to quickly recap, essentially, without solution, your data access and the ZK proof are generated by users themselves locally, and we're license free, which means we don't need API to adapt to new data source, and that makes us very, very scalable. So essentially you can see the new kind of flow chart here. Instead of me submitting that passport bio page, essentially what I need to do is, so here in Australia, we have what we call MyGov Australia, which is like the government official website that has everyone's digital ID. So essentially what I need to do, obviously that's a government website, so it's a trusted data source, right? All I need to do is to log into my MyGov Australia with the zkPass kit switched on. And then obviously I tell zkPass that I want to verify I'm Australian, I'm over 25. And then, my MyGov website is going to return with all my personal info. And then we will generate that credential, the aforementioned, locally. The fact that I am, of nationality Australian, true, over 25, true. And that ZK credential can then be passed on to whatever business platform that wanted to verify that. And here we have two kind of like a simplified technical process flowchart. It might be very hard for you to read, but don't worry. So the left-hand side one is to show you what we did to enable the multi-party computation. So essentially what we did is we redesigned TLS, transport layer security, and turn a two-party handshake into three-party. So instead of the traditional way of me, user, talking to the website, MyGov Australia, and we're essentially the zkPass node and myself bundled together talking to the user. So, we log in pretty normal. The website's going to return with my data, and then with the data that it comes back, we will encrypt it twice with both an encrypt key as well as a MAC key. And the encrypt key essentially makes sure that the zkPass node doesn't really know what exactly data that was coming back, the user's data, and hence that protected user's privacy. And the MAC key is what we call a data integrity key. And that's how we prevent the user from cheating, because whatever the user try to do to tamper with their data, the zkPass nodes will know because of that MAC key, the data integrity key. And on the right-hand side is the process of ZK proof generation. And obviously, I want to highlight that our speed of generating is right now sitting at around 16 seconds, 16, which is a lot faster than a lot of the other kind of like ZK solutions. Like if you're familiar with them, most of them takes over 1 minute. And for us, we're working very hard on the optimization, and essentially we're using interactive kind of ZK computation, and that enabled us to greatly reduce that computational speed. And we're still working on further optimization, and we're aiming to bring that further down to around the 10 seconds kind of level. And we believe that's actually making us hopefully more commercially viable than other solutions that's gonna take over 1 minute for each kind of like ZK proof generation. And here's another example of, for example, if today Compound tells us, hey, Annie, if you can prove that you have, let's say, over hopefully $500,000 cash sitting in your bank account, then that's a proof of your real world asset. And then they can give me a very good lending rate, right? So in that case, what I need to do is I will need to log into my internet bank account, let's say BAML in this case, and per normal, right? Just using my username, password, and then BAML's going to return with account name Annie, account balance X amount. So we will need to tell zkPass, hey, zkPass, please help me verify that I have over $500,000 with BAML. If the answer is yes, then we will generate that ZK proof, well, yes or no, regardless, right? We'll have the ZK proof generated locally, which then can be passed on to Compound for verification, for them to decide whether I can get the best lending rate or not, and credit limit or whatsoever. So why do we call ourselves composable? Because there are, multi-dimension to one's identity, from the very basic, your legal identity, who you are, how old you are, where you're from, what's your nationality, to your degree verification. I graduated from LSE. I would have a LSE alumni login, and through that I can essentially verify that I'm actually graduated from LSE. Your DAO membership, you can verify which DAO you belong to, and etc. Your employment history, your Twitter KOL, if you're a Twitter KOL over, let's say, 20K followers, right? I want to tell people, I want to prove to people I will be able to easily do that. Verify credit score. If I want to verify my real world asset, my internet bank account balance, without telling them exactly how much I have, I will be able to do that. So because of the breadth of kind of like the data source that we can adapt to, which we hopefully want to build the #1 application for Web3 identity pass, right? So we're not really a DID project. We're more than that. DID is like mainly on-chain only, but we can adapt to on-chain and off-chain data source, right? And here's just a list, but not limited to that, obviously. So essentially anything that's web page based, if you have a login, you can prove that. And here are a list of use cases that we will be able to adopt. And from the very basic and straightforward customer onboarding, ZK KYC compliance, to anti-Sybil attack, whitelist distribution, soulless distribution, professional networking, credit score check, educational background check, very, very high level of user profiling. Imagine, like a LinkedIn or like a dating app where, whatever people say are actually true. Whether when I say I work for 10 years at Microsoft is actually true, whether I graduated from Ivy Leagues is true, right? I will be able to achieve very accurate and very high level of user profiling. I can specify, I only want to match with fellow Ivy Leagues people and etc., whatever it is. And here is a quick chart of our business model, but essentially we will be able to face not just the business user side who has verification needs, right? It can be a project that goes, hey, zkPass team, can you guys help me verify that our users are not from a certain jurisdiction, which is actually a very common verification needs for a lot of the project. They're just like, we can't really deal with, like users from American or China or whatever it is, right? And on top of that, we can also have individual users who just want to, mint kind of like identity SBTs just to tell people, I'm actually a Harvard graduate. I'm actually, a developer at Microsoft, et cetera. And here are some stats of our, social media followers, and we were very lucky. We were part of the Binance Incubation Program Season 5, where they selected 12 projects, I believe, out of 900 plus. And we came first in the final demo day, which was, a great kind of big stamp of approval to our tech and our kind of like business case. And on the right-hand side are some of our milestones. We are launching our pre-alpha testnets these 2 weeks, and alpha testnet in Q2, and we will be on mainnet V1 EVM compatible in Q3. My teammate just prompt me. Actually, our latest stats on Twitter followers is 70K. So instead of 45, I need to update the slides. And here are a quick intro of the team. We actually got our core team members on the call. We got Bing, he's our tech lead, and Josh, he's also one of the co-founder. We got Dr. Sherry Xu. She's our kind of research advisors. She's a cryptography expert. She's a lecturer at actually here in Australia, UNSW, and also a PhD researcher from Delta 61, which is quite a prestige research institute here based in Australia as well. I got myself, Annie, on the call, as well as Ryan, Valerie from the BD/marketing side. And obviously, we have Bing, who's like ex-senior engineer from NTT Docomo, and Josh, he also has multiple, he graduated from with a PhD from University of Missouri, and has many years working not just in the States, but also China and globally. And, quite an ambitious slogan, I would say, but we want to definitely bring more people, more potential ZK users into the space. We want to be that bridge between Web 2 and Web 3 world, which is very important because we think, the next batch of projects that's going to come through and survive through the cycles are going to be the one that's trying to bridge the gap between Web 3 and Web 2 world. So yeah, essentially, simply put, we can verify everything for not just Web 3, but also Web 2 world, as long as you have a login to a portal, to a web page, and that will do. And yeah, that's it for my presentation. I would like to play you guys a MVP demo. I think I'll play the one that shows you have over X amount of account balance in our example is from ANZ, which is an Australian bank. And which hopefully will give you guys quite a straightforward idea of what we're trying to do. 1 second. Okay, let's see. Here it is. I definitely have way too many windows open. Can you guys see it?
Yes.
Yep.
Yes. Okay, perfect. Okay, so essentially, I'll just talk it through as we go. So essentially what you do, this is the MVP version. So, don't mind the kind of like simple interface and kind of UI, which will be obviously optimized as we go. So essentially in this example, I click Mint ZK SBT, and then you're gonna come to here, which you tell zkPass, okay, hey, I want to mint a financial SBT from anz.co.nz, which is actually the New Zealand ANZ website. And obviously this is how we make sure that you're grabbing data from the verified data source in the first place, because we will maintain a list of, the verified data source. So it can't be a phishing website or whatever it is. So, it's trustworthy data source from the beginning already. So we tell them, essentially, I want to verify that my available balance is over $30. It can be 30, it can be 300K, it can be 3 million in this case, whatever it is that you specify. And then you click Mint Now. Essentially, you need to log in to your internet bank account at ANZ or BAMO or whatever it is. You log on with your username, password, per normal. And then that's gonna, come back with your data, which then we will start the multi-party computation from here. And this is quite we try to tell you what we're doing at the back. So here you see it's going at already done with the MPC part. And then this is the ZK proof generation part, which, like I mentioned, it takes us around 16 seconds right now. And you can see it's going at 40%, 46, 50 is actually very fast. And voila, the ZK proof is generated, and you can see it in your wallet. And if you click into it, you will be able to also see it on the chain. Yep, so you can, let me just pause here. You can see that, okay, we have SBT that's, it's minted. It proves that my data source is ANZ Bank, anz.co.nz. My available balance is over 30. And essentially in the future, right, you will have multiple dimensions of your SPTs, stuff that's, about your legal identity, whatever it is, right? Not just financial, it can be multi-dimensional. And then you click into it, you can see it on the chain, freshly minted. And yes, that's essentially what we're trying to do. And thanks, guys. I'll hand back to you, Sona, if you have any questions or from the audience.
Yeah, let's open up for questions now. Andreas, you have your hand up. I'll hand to you.
Yeah, so I'm quite curious. Actually, multiple questions, but I'm trying to restrain myself here. The initial commitment, the issuer of the credential, right? The issuer of the credential is what entity? The zkPass node or the actual data source, the ANZ Bank, for example? Are you deriving the commitment based on the digital cert from ANZ? Based on the initial handshake?
Yeah, so essentially, so whatever the trusted data source comes back with, your data on, let it be your account balance or the fact that I'm Australian. So I would say, yes, the credential will be in the form of, you can see that the data source is this is what I'm trying to prove. So I would be saying,
is this signed, right? Are you using the signed by the public key of the cert? Because otherwise you can spoof the shit out of everything, right? Right. I mean, I can pretend to be Google, right? Unless I actually I'm signing something with a public key that has been issued by the Google CA, right? Otherwise it's like, who cares, right?
No, definitely.
So our approach is slightly different from the issuer side. Let's say issuer has the key to sign it. Our approach is more like a TLS level. So it will be, number one, we do not need authorization from a data source for user to issue this credential. That's the major difference. In the traditional way, let's say, okay, you need those data sources to authorize you are able to issue a credential based on my data source, right? That's is not user-centered. So the proposal from zkPass would be, okay, user-centered, basically, okay, user own account on your data source. So which means that this is piece of assets you have. So what zkPass does is, okay, we help users, okay, to to reach out to their data source without any authorization, without any API, without any kind of like a signature from the data source side. So, but we do have a mechanism to prevent the user from like cheating. Number one, it could be a fake data source of Google, as you said, right? But we do have like a template. Number one, we have a template. Okay, we need to audit it to make sure, okay, you are logging into a real Google website. That's number one. Number two would be, okay, while user is kind of like picking up the data from a data source, there is a potential for user to forge the data. Let's say I'm actually 25 years old and the data source. It's possible user wants to forge it back to like 18 years old as young, right? So we do have, that's why we have this multi-party computation decentralized system to prevent the user from forging that data. So, okay, so number one, the data source is trustworthy, right? We do have a template to verify and to make sure it's not a fake website. That's number one. To make sure, okay, Annie is logging into a real MyGov ID website. That's number one. Number two.
So how do you do that? How do you actually technically do that? I'm really interested in that because the only way to actually do that is to know what the key in the X509 is, and then compare that to a public registry, because it's like otherwise it's like you can't do anything, right? Like boom.
Yeah, actually we checked the certificate from the website. Yeah, because actually each certificate will corresponding to one exact website. And during the handshake, we will also check the signature, which is sent by the certificate, the private key in the certificate. So we can make sure that you have exactly access the real data source.
Okay, so you're actually in your circuit, you're actually then verifying the signature of the right?
Yeah, in the certificate. I mean, actually, almost all the websites will use HTTPS, and they will.
Yeah. It's like
they will apply
SSL cert, right? It's a standard one, right? It's a standard SSL cert, but you have the package that is returned that contains the data that has the signature over it, right?
It's not about the data, but only the certificate.
Right, you're validating that but still there's you should, don't you verify that the cert, that the signature is actually valid in the zero knowledge proof? Because otherwise you telling me that you verified the signature doesn't mean anything, right? It's like unless I have the signature itself, then I can verify that the signature that you're claiming comes from the website actually came from the website. So the only way to do that is to actually verify the signature in the circuit. Otherwise, it doesn't work.
It's not the signature in the certificate. The certificate will have a private key which belongs to the actual the corresponding data source. I mean the website. So during the handshake, the website will use this private key to sign the handshake data. I mean, during the TRS handshake. So we just need to check because we have the public key of the certificate, so we can check if the signature is right or not.
Right, but if you're generating a zero knowledge certificate off of that data that you're receiving, right?
No, we don't generate this zero knowledge.
The user generates a certificate.
The user will not generate this part. So our node will check the certificate.
Yeah, that's clear. The point is, let's say if I'm compound, right? What's the predicate that I need to that I actually need, right? I need to know that the identity of the user is there, right? So, and that the issuer is authentic, right? And that the balance is over, let's say, 500K, right? So in order to know whether in order to know whether the signature is authentic, right? And that the data actually came from that data source, I need to verify the signature in the circuit, because otherwise, as compound, that your node verified a signature doesn't mean anything, right? Doesn't mean anything. I can't verify that you verified the signature unless the circuit verifies the signature, and then I can verify the circuit, and then I can trust.
No, actually, we don't need this. This is a different approach from us. So what we want to use, how to prove this data is from like the real data source is we does this on the TLS level. Just when user log into their account and the data source, this is, we treat this, you can say, okay, this is a piece of like a signature if you want to say that way. So it's okay if user able to log into, number one, we already made sure, okay, this website is trustworthy, right? It's a real website of a BOA. That's number one. Number two, as long as the user is able to log into their account under Bank of America, we treat this as a signature from the Bank of America side. So this signature is done by the TLS level. So that's why Bank of America do not need extra signature and the data which user pull out from the data source.
Yeah, I understand. You're using the signed. You're
when you log in,
when you log in with the handshake that's signed, right? You use then you use Diffie-Hellman key exchange to generate the internal encryption key, right? That's what you do. So it's like, and then the data is returned, but initially you have the encryption by the key, and you have an initial signature that's verified in the initial handshake.
That's correct. So with over the TLS level, it's okay. There is an access token. So when user log into the Bank of America website, any website, there's access token, right? So access token, you can see is one type of like a credentials. Okay, so the server side, the Bank of America server side, because there's kind of like a credential side. Okay, just pass it over to verify. Okay, this is my user. Okay, he or she is able to have access to my data source. So that's how we are able to, or user is able to get those trustworthy data from the Bank of America. So in this sense, okay, so after this, so this is a TLS. After the TLS level, okay, Bank of America already authorized kind of this user is able to kind of get their data source from Bank of America, and then
understood.
That's okay. So that's the TLS level. Once the TLS level is passed, okay, we move on to the MPC, multi-party computation, like second stage. So this stage is because user now have already authorized to get to the data through the login. Okay, so the second step would be there's a potential user is able to forge the data now, right? So that's how we move to the MPC multi-party computation. Okay, we have two keys, and one is encrypted key. Another one is the market key. Market key is the data integrity key. We do not want the user to forge this data. So once the MPC is down, it's finished. Okay, we move on to the zero knowledge generation period. So that's basically the whole process. That's why we, as you said, we do not need any signature, to be on the zero knowledge side.
No, I'm not saying that you need to sign the zero knowledge proof. If I am the verifier, the zero knowledge certificate verifier, right? I need to know that the site from which the data comes is authentic, which is the signature that the site not generates from the over the data that it's received. It's from the initial handshake, right? Where the site, the ANZ Bank digital digital cert has signed the initial handshake, and you're verifying that it belongs to this URL. And that's all you need. But in order for me as a verifier, certificate verifier, to trust, right, that the circuit itself needs to verify that initial handshake signature from the digital cert of the issuer. If you don't have that, it's like, then I need to trust your network. Why would I trust your network? Right? It's like
that's what we're doing in the first place, right? So like the first thing of essentially once we, we're doing a 3-party handshake, right? The first thing we do is obviously, that's the legit URLs, and then we check the site signature, like being mentioned, and we're essentially doing that like very first thing, right? Before we even, So so to you, that's not enough, or
no,
like you?
It's like I need to know that you actually did it, right? You telling me that you verified the signature doesn't mean anything. It doesn't mean anything, right? So I'm just not. I'm not being
so like obviously in the future, I will be like. Well, no, totally. I love the enthusiasm, and happy to discuss it.
No, I've done this for like over a decade. This kind of stuff.
Like,
so it's like.
Yeah, essentially, how do you trust it? Like, we will be open source, and obviously everyone can audit it, and we actually will have periodic audit of a list of like the trusted data source that we maintain, and everything will be open. If you want to know whether are you actually running a decentralized zk node network, you will be able to do that. If that's kind of like to somewhat extent, we'll be able to help people. Knowing how we're doing things, how the process goes, what we're verifying, how we're making sure that we're getting data from trustworthy data source, and take it from there.
So your zero knowledge proof is what? A snark, a stark? A snark, right? Since you're verifying it on chain.
It's zkSnark.
It's a snark, right? So
Yeah,
is it what you're using Plonk or Graph 16?
We're using Plonk.
Plonk. Okay, so trusted setup is ignition. Great, perfect. So what I'm saying is that if you think about converting, a certificate like a verifiable credential into a data structure that you can actually verify in a snark, right, or in a circuit. Right, more generally, right? One of the key things is that I need to know that the website you're claiming, right, is the website that this data is coming from, right? Actually, there is a handshake proof with a signature from the site. So the public data consists of the URL and the public key, of the site. Besides the public key of the user, right? Those are at least 3 public input sources that you need for the snark. But if you have that, then you can verify the actual signature, right? In the circuit. So if you do that, right, then you can verify. Then you have assurances, right, that there was a signature and the signature is correct, right? Because otherwise I need to trust your network that you verified the signature, right? And why would I trust your network, right? It's like because there's no trust assurances unless you have like, oh yeah, we did it, and here is the consensus protocol, and that has this many security assurances, and I can verify your computation, right? Otherwise, it doesn't work, right? Otherwise, it's not trustworthy.
I think maybe we can go back to Annie. Can you just go back to that very detail? Yes. Maybe zoom. Maybe
can you like zoom in? Yeah.
Zoom in a little bit. Yes. Zoom in. Yeah. Sorry. You probably need to get out of this like a presentation mode, and then zoom in. exit.
You do it like at 200 or something like that.
Right.
Zoom into like, yeah, if you go like on the loop on the right next to the down there on the go to 200% on the magnification, right next to the to the roller, all the way to the left hand side, up, up a little to the right. Yes, there.
You
there
got
you
it
go.
there. Yeah.
To
Yeah,
200 or 150 or something like that. 100.
Yeah, you can maybe drag a little bit. Yeah.
You can drag it a little bit over.
Right.
Oops.
Oh.
Maybe a little too much. Just go back onto the magnifying glass and go to 100. Yes. Right, perfect.
Yeah, and maybe let me do the. Can you let me show my screen? I think mine is. Yeah, maybe just let me. Yeah. Hello.
Yes.
Annie, you mute yourself. Yes, you mute yourself.
Oh yeah, I said I stopped sharing because I can't
it's all
really.
good.
On
Okay, let me share my. I think this is much clearer here. All right, so can you guys see?
Yes, can see.
All right, perfect. Let me just get rid of this first. Okay, so here is basically okay, sorry, so basically the whole kind of like interaction we divide it into like 3 stages. The first stage would be the TLS, right? That's how you get a subject, and then so that's how you see you get the register, you choose the template. So this template it's the specification. Sorry. So this template is kind of like what that's a compound. Okay, what you need to verify your name, you need to verify the bank balance. That's what's in the template, right? And then you send it over the KYC entrance. You get this URL, and then direct to zkPass, and that's basically the first step. And then what's happening here, I think that's what you are asking or wondering is here. So the whole TLS, how we can flag the user. So the first
can you
step,
zoom in a little bit more? Can you zoom in a little bit more? Because that's perfect. That's perfect. So I think everybody can actually see it. Right.
Okay.
Got it.
So yeah, number one is we mentioned like we change from traditional like 2-party TLS client server, like a user and a server, into 3-party, into like by saying 3-party, we add this zkPass node as 1 party. Okay, so this V and the P working together as 1 party and talking to the website side as a server, right? So the first step would be, okay, they do the client hello into the handshake, send over the inquiry, and then the website side, response back with the credential. Yes, with the credentials, right? And then once we have these credentials, okay, now, so the P, the user side, and the V side, they both generate this public key, and based on the responses from the server side, you can see, this pre-master key, and that's how it generates. And then once this, so each V and P, each side generating their public key, and then now, okay, so step 5. So there will be a combined the pre-master key generated from based on P and V. So this combined the key and as 1 party talking to the server side. And then server with the server side. Okay, server kind of like recognize this like a pre-master key. So that's how you see PMS would be the pre-master key secret. So generate this pre-master secret based on the responses from the server side. And then, so this is basically the whole TLS level. So that's how, the server side is able to recognize, or even, to recognize the user side from this certificate, the certificate, the server issued, right? And then, so that's the TLS. Once this is over, okay, so the extension will help to generate this pre-master secret. So you can see, okay, the server side pre-master secret S would be the pre-master secret for the server side, and also this would be the pre-master secret for the prover side, the user side, and also here it's the pre-master secret for the verify side. So that's how, okay, with this pre-master secret, we do have like two keys. One is, you see the encrypted key here. Second one, so while this server has a response, we have two keys, the encrypt key and also the market key, encrypt key, right?
Yes.
And the prover side has both the keys. Why? So encrypt key is just to encrypt this responses from the server side.
Correct.
And then the prover only has the key, the market key. And then if you take a look at the verified, the node side, the node only has this market key. Only has the reason the node do not have this encrypted key, because we do not want the node to have access to the,
correct,
this response to information, right? That makes sense, right? Okay, so now, so each party may have this market key. So at the end of this, the MPC side, we need to check this H mark. We need to check this market key. This is encrypted, okay? We need to here step 9. Okay, we need to check the H mark. This is the market key. Okay, we need to check this mark. So eventually, and then we encrypt this whole thing, and then as a commitment. So step 10 right here. So you see the whole Q dot, which is the query side, R dash, which is the the responses from the server side, and yes, and then we have this market key here, right? Market key, which means, okay, if a market key is verified, which means the prover, the user side, cannot change this data. Okay, so that's a step 10. Now 11 side, okay, we check this market key. Okay, we check this market key, and then so both the party are going to able to verify, okay, did you change the data or not? So we need to verify this mark. That's how it is. So once you check this market key, okay, we are able to decrypt. So the user side, the prover side, is able to decrypt this crypted information, right? So that's how basically user now, okay, through the TLS, through the MPC period. Now, okay, user is able to generate this. So that would be the next step, which would be because okay, we check the market key. Now user do not change the data. So okay, now it's about the time to generate the zkP now. So in terms of the zkP, okay, even before even the generating, so over the zkP period, we do have this few constraints. If you look at that, so that's these constraints are the ones, as you mentioned, that's probably what you're wondering. It's where is the signature? Here is the kind of like the signature you mentioned. Okay, over this zkP generation, we do have this verification of the constraints. You see, the first constraint would be, okay, we need to verify this encrypted key. You see that one, right? Encrypted key. So this is to make sure, okay, this data came out from Bank of America and is encrypted. Second one, we verify. You see, second line is the market key. Market key. Okay, we need to verify does the user change this market key or not. We need to verify this is true, right? And then after this both verified encrypted key and market key, okay, now it's about time to this is the asset which is that's to make sure this URL is the real URL we refer to, which this is to prevent the user from say, you are logging into a fake website, whatever. So that's the way to do it. And the query is just the template set of the name, the bank balance, right? Okay, with all this verified, now, we generating the proof of zero knowledge. So that's okay, you get this proof, and then you transfer this proof to the compound side. That's basically, and then once you have this zk knowledge generated, okay, compound just verify the zk knowledge through the on-chain smart contract. That's basically how the whole flow. Yeah.
So from B, X, and W, which X is the public which is the public input? What's the private input? Here, it should be the W is the public input, right?
W is the private input.
It's a private input because it has the encryption key, right? It has an encryption key, token Q and R. So X should be the
public input.
X is the public input, right? Oh, okay, got it. All right, great. No, I was just wanted to make sure that I'm not dreaming here. No, that yes, okay. So I understand because the commitments are generated off of the response from the website.
From the website, yes. And then we get a system to number one, encrypt. Second one would be, okay, there's a market key just to prevent those guys from cheating. Yeah. That's
Also, just since we're running low on time, Otto, can we address your question?
Yeah, sorry about that. I didn't mean to like hijack.
No, it's good. It's
okay.
good. It's good.
It's really good. It's really good. Yeah, that's great. Yeah.
Yeah. So just to contrast your approach, it sounds like it's a little bit similar to what Gitcoin Passport is doing, in a sense where you have this source that you get some data from, and then you just issue this credential that you can check. In your case, it's a proof, right? So you would be maintaining, I guess, a set of templates from various sources that you trust. You mentioned like a bank and so on, and then the person would sort of self-issue this proof. Like, is that what you're sort of doing? Can you contrast it maybe to Gitcoin Passport a bit?
Yeah, so we do need to maintain kind of like a template, because the reason for the template, number one, would be, okay, that's why we need to make sure that's a trustworthy website you are using. That's number one. Number two, the function of a template would be, okay, we only want the user to disclose the information they want to disclose. Let's say the age. If you go to a bar, okay, they only need to verify you're 18 years old. Somehow you just submit your ID, contains age, name, address, even color, whatever. Too much information disclosed. That's why we have this template. Okay, you just need to be very specific what type of information you want to verify. No extra information disclosed. Yeah, and so that's kind of like we can doing this with okay, it's user-centered, and also it's a little at the individual level, you just mint your zkSBT as you want. What type of information you want to verify? That's it. And so compare.
Sorry, one quick question. So the verifier needs to still trust that the initial MPC between the user and zkPass was correct, right?
Yes.
The initial computation. Ideally, you would generate a zkP for that, which you could, and because you can, the private key could be the private input, and then you can verify that the computation was done correctly. You can do that, and then you recurse. Then the witness becomes an input into the circuit. So you actually, then you need a recursive circuit, obviously, but it would prove that, because right now the trust point, right? Everything is trustless. Everything's fine if you because you can verify that the keys generated used, if you want to go through that trouble, is actually from the website, from the digital cert, etc. The trust point is then still the multi-party computation between user and zkPass on the initial shared secret that you're that you're generating that is then included into the as a secret in the handshake for the between the user and the website.
Yes, actually the MPC side is it's just to prove user did not forge the data from the data source side.
Yeah. You still need to prove that the input data that you used for the authentication is correct, right? So it's like ideally right now the trust point is that zkPass isn't cheating, right? So it's the either you have a there's no collusion between the user and zkPass. So ideally you would have a proof that the computation, right, that the Fiat Shamir secret sharing step was done correctly, and then you include that into every other proof that uses that initial shared secret.
Yeah, that's correct.
Yes, you are right. Yeah.
Right. So
we use
which is okay.
Yes. So first, I think all the node for this task, each task, they will be randomly assigned during the in the contract. So there will be a real possibility to assign for some malicious, for some adversary node, and also we use an adversary protocol for the MPC. So which means, if there is one node which is semi-honest and this task it can be detected if other node they may be adversary. So we can directly stop this task, and then maybe user had to retry it again. And but for the whole process, so there will be very real possibility. So they will get all the node to be adversary. So
right now you need coordination between the nodes to verify that no node cheated. If you include the proof, then you can just have nodes, right? That are executing the same code, and you can check that it is done securely. You don't need to cross verify. So you're reducing your trust assumptions, and this is really what you want to do, right? You want to minimize your trust assumptions, ideally to zero.
Yes, that's true.
Anyway, just
all right. Yes, we're a few minutes over time, but there was lots to discuss. Thank you for coming on and sharing and showing and walking us through what you guys are working on. I feel like we will need a part 2 in the near future, because we didn't even get too far into things like the use cases and different partners or projects you're working on at the moment from those different use cases that you explained. So it would be great to have you on again in the near future. But thanks for joining this time, and we'll see you in the baseline community, hopefully.
Yeah, so it would be awesome.
Thank you for inviting us, and for a lot of the question that we didn't get to address, I think we can take that, to like the chat group or whatsoever, and then we'll come back on that.
Sure.
Awesome. Yeah, I will send you an invite.
Great job.
To the baseline
Thank
Slack.
Thank you, guys.
Thank you, Andy.
Yeah, thank you, guys. Very, very interesting.
Very cool.
Thank
you.
Cool have a good day, everyone.
Good luck.
Have a good
Cheers.
day.
Goodbye, everyone.
Thank you.
Thank you for joining us.